All right, we're back with a little bit more physics here. This time we're going to be looking at kinetic energy and collision. So, what happens to kinetic energy when it collides with something else? And the answer is that while energy is conserved, which is the law of conservation of energy, while energy is conserved, it is changed into a lot of different things. So kinetic energy is sort of one form of energy, and so when things collide, it's often very much possible that the energy will go into things such as heat, such as potential energy, maybe in some form or another. Maybe it'll get transferred into some kind of elastic energy, or something that basically any form of thermal energy that causes it to what we would call be lost or enter into entropy. But so the idea is that the energy is never lost. It always goes somewhere, but it doesn't necessarily continue as kinetic energy. So when two things hit each other, they may essentially lose some of that kinetic energy to other things. So we're going to look at the three types of collisions and how we track kinetic energy flow through them. Now, another thing that we want to consider in looking at this is the idea of mechanical energy. And we're going to do some problems later on to show this. Now, mechanical energy is the idea of how energy flows in and out of the things that go into the air. So we have energy, mechanical energy, that's what that is. We'll just call that E, equals the sum of all the kinetic energy plus the potential energy. So, for example, you have a ball go into the air. Initially, it starts out all kinetic energy, and at the very top here, when it slows down to zero, it's all potential energy. And so then anywhere in between, it's going to be a combination of kinetic and potential. And so this stays fairly conservable in the sense that we can usually track the change from kinetic to potential as we go up and down all along. And that's how a roller coaster works. So if you ever rode on a roller coaster, it goes up really high to begin with, and then after that, it goes up not quite as high. And this is a fun roller coaster. Look at that sucker. And then we get off and we go get on again. But so here's what's going to happen. The initial input of energy takes it all the way up to the top. So that thing starts with all potential energy, right? And so that potential energy is going to go all the way down to the bottom, and then right here, all of that potential energy will have transferred to kinetic energy, right? Which that kinetic energy is enough to send it soaring over the top of this, back down again, and so here we have some kinetic plus potential. Plus potential energy right here at the top, so we're still moving fast and we're gaining height. So back down here again, we've transferred all the kinetic, and then once again we have a combo, back down, back down, back down. Now, of course, in a roller coaster, we lose a little bit every time. Why? Because stuff is happening where, like I was mentioning earlier, where the energy is going into different forms. So the energy doesn't stay necessarily in this system. We got heat transferring to the tracks, we got friction, we got air resistance, we got all sorts of stuff happening where energy is actually being consumed as it changes into other forms, or we could say lost from the system. So essentially what's happened is, if our system is the railroad car, some of this energy is going to the outside world and not staying in here into the mechanical energy. But if you are analyzing, just a simple situation of something going up in the air and coming down, for the most part, the energy is going to stay in that system and not get transferred to the outside world. But even in the situation with the ball going up and down, you're going to encounter some air resistance. Or you may have seen those Newton kind of little clangy ball things, whatever. So you take one, move it up, and boom, it transfers all the kinetic energy out, and this one goes up. Even this will eventually slow down. So what's happening here is the kinetic energy is being transferred to potential energy, coming back down, hitting this. The kinetic energy is transferring through this by way of momentum. and then boom, the one on the end transfers out and then back down. So we have this exchange of kinetic energy, which turns into potential energy and then comes back down into kinetic energy. But every time these things whack each other, they're losing a little bit. So this will eventually slow down. Right? But that's kind of a neat little experiment. It's about as close to conserving all this kinetic energy as you can get, right? All right, so let's look at some examples then, real quick, of the different types of collisions. So this is the idea of different types of collisions. And so I'm going to show you 3 kinds of collisions, and we're going to look at how we track momentum and kinetic energy and how we can use the two and in collisions to sort of find things. So the neat thing about momentum, so momentum is P initial equals P final, and so it's going to be a mass times sorry about that. It's going to be a mass times a velocity, right? Equals, an ending mass times velocity. Well, kinetic energy, right? Kinetic energy equals 1/2 mass times velocity squared. So clearly these things have very much in common, yet they're a little bit different. So we can use them interchangeably to figure things out, like by way of kinetic energy. Let's say that your system loses kinetic energy, which most will. You could actually track how much kinetic energy you have afterwards, and then you'd kind of maybe even have an idea of how much energy went into things such as heat. And so if you kind of knew the other form of energy that something went into, what didn't come out the other side, you would know is what changed form into something else. So let's look at this collision right here. So here's 2 balls, and so this ball A whacks ball B. They both weigh 0.25 kilograms. They don't seem drawn to scale, but that's because of my superior drawing skills. If this ball whacks this one, and say this one is going 2 meters per second, and after that this one stays still, and that one flies off at 2 meters per second. Well, we clearly have conservation of momentum. That's very easy to see. And so if we calculate that out, 0.25 times 2 plus, so this is the momentum initial is this scenario here, it should equal the momentum final, and sure enough it does. So basically 0.5 equals 0.5, right? So if you calculate that out, all the momentum's initial equals all the momentum's final. And that's pretty easy to see. All we did was transfer that velocity from one ball to the other. They weigh the same. Now let's look at kinetic energy. Kinetic energy is also conserved in this situation. So if we look at the kinetic energy initial, if we analyze this, we're going to have 1/2 the mass of A, so 0.25 times the velocity of A squared, right? And it's going to be plus 0 because this one has a velocity of 0. And if we analyze it afterwards, this one's going to be 0, and this side of the equation is going to be exactly like this side of the equation over here. So what we find is the kinetic energy initial, all the kinetic energy here, 1/2 mass times velocity squared plus 1/2 mass times velocity squared here, equals exactly this, and they're both 0.5. Now let's look at a different scenario. Now what happens if I have ball A and it whacks ball B? And let's say that ball A flies backwards after it hits it, and we have the same initial velocity, 2 meters per second. And let's say ball A flies backwards at negative 0.2, and ball B flies forward at 2.2. Well, let's look at our momentum. So our momentum here, we have 0.25 times 2 plus 0.25 times 0. So there we go. So that's just going to be 0.5 overall equals 0.25 times negative 0.2, because this one's going backwards, plus 0.25 times 2.2, also 0.5. 0.5 equals 0.5. So once again, we see that momentum is still conserved, right? Because in momentum, we're just looking at mass and velocity only. It's not really taking into account this whole energy thing of energy flowing in and out of the system. It's just the mass and the velocity is what momentum is. So almost always you will find that momentum is conserved. But kinetic energy, not so much. In this case, kinetic energy actually increases. So if we look at the initial, here's our 1/2 mass. We know that that was 0.5. We calculated that earlier, right? But if we look at our kinetic energy final, 1/2 our mass, so 0.25 times negative 0.2 squared plus 1/2 0.25 times 2.2 squared equals 0.6. So if you look at this right here, what actually happened was our kinetic energy increased, right? So our kinetic energy initial, right, was less than our kinetic energy final. And so what we call here, this situation, is we call this a super elastic collision. So a super elastic collision, pretty simple. The kinetic energy increases. Now you might ask, why is that? Well, probably one of the most easy explanations would be that some of these two balls had some kind of elasticity, in the sense that when they collided, the kinetic energy was transferred into elastic potential energy, which then sprung out and added even more energy to the system in addition to the initial kinetic energy. That's probably what happened. So, and maybe not. There's other situations that could have this as well. If we go back to our one over here, what do we call this? If it was exactly the same before and after, and our kinetic energy was exactly the same before and after, these are called elastic collisions. Now in chemistry, you learn about the kinetic energy of gases, and we also learn that when a gas particle hits another gas particle, it's always elastic. Kinetic energy is always conserved in the case of the kinetic molecular theory. So in the case of gases hitting each other as they go along, they don't lose kinetic energy. They don't get they don't have this sort of inelastic, super elastic problem. They're always elastic collisions. So that's something that you'll learn in chemistry, and so understanding the physics of it is pretty cool. All right, so one more situation right here, and then we'll do some example problems after that. But here's my last situation. So I have ball A and ball B, and ball A whacks ball B. Same situation, our initial velocity is 2.00 meters per second. Now this time, the balls, when they collide, they stick together. They smash together and become one moving mass that then moves, and let's say that there's no friction in any of these cases, of course. They move at 1 meter per second. Now this makes sense. Look, we've got the one ball that's half the mass, hits the other ball. Now the two balls with twice the mass move at half the velocity. So if we look at my momentum initial and momentum final, sure enough, 0.5 equals 0.5. So once again, momentum is conserved. But when we look at the kinetic energy, we have our kinetic energy final. We know that that's 0.5. Or our kinetic energy initial, we know that that's 0.5. We looked at our kinetic energy final. 1/2 of these two masses together times their new velocity squared equals 0.25. So what happened? Our kinetic energy went down. So my kinetic energy initial, in this case, was greater than my kinetic energy final. So what do we call that? We call that an inelastic collision. Now, oftentimes, this is what you find. And why do you oftentimes find this? Well, most of the time, you have a situation like this. And what might have caused this? Well, if these balls were kind of, let's say, more like clay balls or something like that, what would have happened in order to cause them to smash together is they would have had to sort of deform a little bit, right? Deform a little bit and then connect together. So there's actually energy that went into that deformation and actually may have transferred heat in there as well. And so that's where the kinetic energy went, and that's why it's inelastic. So, most of the time, and so actually when you have cars, cars crash into each other. Okay, let's say in this case we have a truck crashing into a car, right? Momentum is conserved, and so what is it that causes all the damage? Well, it's actually probably this kinetic energy bit. So we had kinetic energy, and everybody was happy. But as soon as that kinetic energy transferred into heat and crumpling up and smashing this car in, now we're not so happy. So it's actually the kinetic energy in a car crash that is dangerous, not necessarily the momentum. And of course, you can't really say that because without the momentum, you wouldn't have had the situation anyways. But theoretically, it was the kinetic energy that did the damage. The momentum just sort of got us there. All right. Let's go ahead and do a couple of problems. And so I'll work out a couple of problems which should be similar to the kinds of problems you'll see on your homework assignments when looking at this kinetic energy conservation stuff.